If you've ever wondered how a graphics card turns complex 3D models into stunning visual experiences or how it accelerates processes beyond just gaming, this video is for you. We'll delve into the architecture of a graphics card, explore its key components, and discuss the evolution of GPU technology. So let's get started. At its core, a graphics card has two main functions. It receives instructions from the Central Processing Unit, or CPU, about what to display, and then processes those instructions using its own processor, called the GPU, or Graphics Processing Unit. After processing, it stores the image data in its dedicated memory called VRAM or video RAM before converting it into a signal that your monitor can understand. Let's take a closer look at each of these components. The GPU is a specialized processor designed to perform many simple operations very quickly. It contains thousands of smaller cores, each capable of processing a small part of an image or video stream. These cores are optimized for floating point calculations, which are common in graphics processing. For example, when you're playing a game, the GPU uses these cores to calculate the color, position, and lighting for every single pixel on your screen. In contrast, CPUs have fewer cores and are better at handling complex, branching operations that require precise control flow. They are optimized for integer calculations and have lower latency, which means they can handle small bursts of data very efficiently. Think of it this way: a CPU is like a chef in a kitchen. It can handle a few complex dishes at once and requires precise control over each step in the process. On the other hand, a GPU is like an assembly line in a factory. It can handle many simple tasks simultaneously, making it perfect for mass-producing identical items like rendering millions of pixels on your screen. Video memory, or VRAM, is a type of random access memory that is specifically designed to store all the information the GPU needs to create an image. This includes texture data, such as the colors and details of a model, frame buffers that store the intermediate results of the rendering process, and other graphics information. There are several types of RAM, including GDDR5, GDDR6, GDDR6, X and HBM, or high bandwidth memory. These different types offer varying levels of speed and capacity and are chosen based on the specific requirements of the graphics card. For example, GDDR6X is the latest and fastest type of VRM currently available and is used in high-end graphics cards such as the RTX 40 series from NVIDIA. GDDR6, on the other hand, is slightly slower, but is still widely used in mainstream graphics cards. The amount of RAM in a graphics card can vary depending on its model, but typically ranges from a few gigabytes to over a dozen gigabytes. Having more VRA allows the GPU to store more textures and other graphics information in memory, resulting in better performance and image quality. For example, a game might require more VRAM if it has a lot of high-resolution textures, or if it needs to render complex scenes with lots of objects. A graphics card generates a tremendous amount of heat due to the high power consumption of the GPU and VRAM. To prevent overheating, graphics cards use cooling systems that typically consist of heat sinks and fans. Some high-end cards may use liquid cooling instead. These cooling systems are crucial for maintaining the performance and longevity of the graphics card, as overheating can cause performance degradation, even damage to the components. Display outputs are the connectors on your graphics card that allow it to send the final image to your monitor. Modern graphics cards typically support current interfaces such as These interfaces support high resolutions, high refresh rates, and other advanced features, such as HDR and G-Sync. HDMI stands for High Definition Multimedia Interface and is a widely used interface for connecting devices such as monitors, TVs, and game consoles. DisplayPort is another popular interface that is commonly used for high-performance computing and is known for its reliability and support for advanced features. USB Type-C is a newer interface that is gaining popularity due to its versatility and support for multiple devices. Most graphics cards get some power from the PCIe slot they're inserted into. However, higher-end cards require additional power to function. This extra power is supplied through 6-pin or 8-pin connectors located on the card. These connectors can provide up to several hundred watts of power, which is necessary for high-performance GPUs that consume a lot of energy while rendering images. To understand how a graphics card works, it's essential to know about its architecture. Modern GPUs use a massively parallel architecture consisting of thousands of small cores grouped into larger units called streaming multiprocessors, or sometimes referred to as compute units or CUS on AMD. Each SM or CU contains multiple cores, each capable of executing hundreds of threads simultaneously. This massive parallelism allows the GPU to perform billions of calculations per second, making it suitable for graphics, processing, and other parallel computing tasks. Memory plays a crucial role in the performance of a graphics card. GPUs use a hierarchical memory system similar to CPUs, but optimized for graphics. The memory hierarchy consists of registers. shared memory, and global memory. Registers are the fastest but smallest memory space and hold temporary data for each thread. Shared memory is a bit slower but larger than registers and is shared between threads within a block. Global memory, also known as VRAM, is slower than shared memory, but much larger and accessible to all threads. This memory hierarchy ensures that the GPU has both fast memory for temporary data and large, slow memory for storing textures and other graphics information. The GPU's architecture enables parallel processing, allowing it to execute many simple operations on datasets simultaneously. This contrasts with the sequential processing of CPUs, which execute instructions one at a time. GPUs excel in parallel processing because each core is lightweight and can execute simple operations efficiently. This makes them ideal for graphics processing as each pixel or vertex can be processed independently without dependencies on other calculations. GPUs are also used for other parallel workloads, such as scientific computing, machine learning, and cryptocurrency mining. Now that we've covered the basics, let's dive into the graphics pipeline. When rendering 3D graphics, GPUs follow a series of steps known as the graphics pipeline to transform a 3D scene into a 2D image that can be displayed on a monitor. The pipeline consists of several stages, including vertex processing, primitive assembly, rasterization, pixel processing, or fragment shading, and output merging. Vertex processing involves transforming the 3D vertex data, which includes position, color, texture, coordinates, and other information into the correct perspective and applying lighting and other effects. Next, the vertices are grouped together into geometric primitives such as triangles, lines, or points during primitive assembly. Rasterization converts the vector graphics, which represent the objects in the scene, into raster images, a collection of pixels that can be displayed on a screen. Each pixel is assigned a color based on the primitives that cover it. Pixel processing, or fragment shading, calculates the final color for each pixel by taking into account factors such as lighting, shadows, reflections, and textures. Finally, output merging combines the fragments with the frame buffer, which is a storage area that holds the image data for the current frame. This stage handles depth testing, blending, which is the process of smoothing out jagged edges to create a more realistic image. GPUs have become increasingly powerful and versatile over the years. One of the most notable advancements in modern GPUs is ray tracing, which simulates the physical behavior of light to create more realistic lighting and shadow effects. GPUs with dedicated RT cores such as those found in NVIDIA SRTX graphics cards can accelerate ray tracing, reducing the time required to render a frame and improving the overall quality of the image. Another exciting development is AI acceleration, which utilizes tensor cores or AI accelerators to speed up deep learning tasks. For example, NVIDIA SDLSS, or deep learning supersampling, uses AI to train a model that can predict the appearance of an image based on a few training samples. This allows for faster rendering of high-resolution images without sacrificing image quality, which can significantly improve the performance of games and other graphics applications. Variable rate shading is another innovative feature of modern GPUs. It dynamically allocates more processing power to important areas of the image while reducing the rate of processing in less important areas. This results in an overall increase in performance without a noticeable loss in quality. By intelligently allocating resources, GPUs can render complex scenes with intricate details while maintaining smooth frame rates. In conclusion, graphics cards have become indispensable for tasks beyond gaming, such as scientific computing, machine learning, and cryptocurrency mining. They're a highly parallel architecture, specialized memory system, and enhanced software ecosystems enable GPUs to excel in a wide range of applications. Understanding the GPU architecture and how it compares to AC can help you select the right graphics card for your specific needs. Optimize software to harness the GPU's power and appreciate the incredible engineering that goes into delivering stunning visual experiences. As GPU technology continues to evolve, we can expect even greater advancements in areas such as ray tracing, AI acceleration, and variable rate shading, further blurring the line between virtual worlds and reality. We hope you enjoyed this video and learned something new about how graphics cards work. If you did, please consider subscribing and leaving a comment below to let us know what you want to see next. And if you're interested in exploring more about computer hardware or software, we have plenty of content for you to explore. Thanks for watching, and we'll see you in the next one.